Sine and cosine represent waves, also known as periodic functions. If you don't know the unit circle, pause the video and figure that out because it directly relates to how we will graph these trig functions. The first question you have to ask yourself when graphing a periodic function is how long is its period, or how long does it take to complete one cycle? So we then divide that into fourths, just like there are four quadrants of the unit circle. For sine and cosine, their period is always 2 pi. These trig functions do repeat, so technically they infinitely go in both directions, but for practical purposes, we only focus on one period since all the information repeats. Once you have the start and end of the period, then you break it down into 4 equal parts. Dividing this by a fourth, in my opinion, is not as easy as just taking half of it and then taking half of that, like the following. Once you know what a fourth is, you could add that to a half to get 3/4, or you could just multiply 2 pi by 3/4 to find this last piece. Personally, because fractions aren't so difficult to add with, I just take a quarter and add it to a half. And you'll notice these are the measures around the unit circle at the quadrants. And from the same tool, you'll know that sine has an amplitude of +1 and -1. Now that we set up the structure of our graph, we will go ahead and start plotting the points from the unit circle. Recall that the sine of 0 radians is 0. The sine of pi on 2 is 1. And the sine of pi is 0. Plotting those points, and then continuing around the other half of the unit circle, the sine of 3 pi on 2 is -1, and the sine of 2 pi brings us back to 0. Connecting the dots will give us a wave. And as you can see, this is one period because we're about to pick up where we started. And this represents the parent graph of the parametric sine trig function. Cosine will look similar, but it has a phase shift of pi on 2. So when we are at 0 radians, we will have a cosine of 1. Take note of how I set up my graph. I start with 4 hash marks for the x-axis, and then I need to figure out what the period of cosine is. Write it here, divide it in half, divide that in half, and then add that quarter to the half. And then don't forget that the amplitude is 1. So I'm almost there. And now I have my graph set up. Notice that it's the same as sine, but instead of starting at 0 for the cosine of 0, we will start at 1. And then the cosine of pi on 2 is 0, the cosine of pi is -1, etc. So those are the points. It's a little tougher to figure out that this is going to curve, so be very careful. Do not treat this like a V for absolute value. Graphed, we could see the wave-like nature of cosine. Because these are periodic functions, they repeat indefinitely, so both of their domains are the set of reals, and their coordinates are typically expressed in radians, as you see here, but they can be represented in degrees and other measurements, depending on context, as we will see in this lesson. Now, the range for the parent graph is from 1 to -1, just like you would see from the unit circle. With a radius of 1, it could only have a max or min value of 1 or -1. Their periods are 2 pi. The amplitudes are 1, and the amplitude, recall, is the distance from the baseline in this parent graph, which is the x-axis, and then the distance to its highest or lowest point. And then let's talk about these x-intercepts. Because these are periodic functions that wave or progress forward and backward indefinitely, then you have to have this n notation where n is an integer. So for sine, because at 0, it is 0. That is an x-intercept. But then after one click or multiple of pi, then you get another x-intercept. And then at another interval of pi, you get another x-intercept. So that's why it's n pi. But notice for cosine that you first have to add pi on 2 because there's a phase shift to get from sine to cosine. They're basically the same thing because one is opposite over hypotenuse, sine, and the other is adjacent over hypotenuse, cosine, but they are related. So here you have to add pi on 2 to get your first x-intercept, and then after that you do multiples of pi. So you have pi on 2 plus pi n. And these are x-intercepts because their y-coordinates are 0. In general, the absolute value of A, the vertical stretch or compression parameter, is the amplitude. And the horizontal stretch or compression factor B, its absolute value, will stretch or compress the period or the horizontal dimension of the periodic function. H, in this context, is known as the phase shift. So it'll actually take the trig function and move it to the right or the left with respect to a certain horizontal reference point. And K is the vertical shift, so then that's going to affect the amplitude because it's going to increase all the y values. And before we take a look at our first example, I want to clarify something. The vertical shift does not affect the amplitude value. The amplitude is always the absolute value of half the distance of the peak to the valley, or it's the absolute value or the distance from a peak or valley to the mid or baseline. The vertical shift will affect the range. So the range of this one would go from 5 to 1, or from 1 to 5. In the first example, we're working with the sine periodic trig function, and we need to start off graphing it. So identifying the transformations first, and then picking out the amplitude and period will actually make more sense, and then we'll use that information to create the graph. The 2 out front multiplies all the outputs of this trig function. Therefore, it's a vertical stretch by 2. And here we are multiplying by 1/3 all the input values. So that's a horizontal stretch by 3. Interpreting these in the context of a trig function regarding amplitude and period. The amplitude of the parent graph is 1. And now that is doubled and will equal 2. And for the period, which is the parent graph has 2 pi, we now triple it. Now that we know what the period is, or how long it takes for the sinusoidal wave to cycle once, we know what the last x-coordinate is going to be for our two-dimensional representation. So as described before, you set up your graph with your 4 horizontal hash marks. This we will label the same value as the period. And then notice I have 2 vertical line segments because the amplitude is 2. I started off with 6 pi, divided it by 2, starting at 0 radians. Now divide this by 2. And now I have a choice. I could either add these 2 together to get 3/4, or I could just multiply 6 pi by 3/4. So it's entirely your preference. And now I will go ahead and realize that because this is the sine graph, I start off at 0, and then I go up to the top of like the maximum value of the amplitude, which is 2. I return to the x-axis. I then go a full amplitude below, and then I'm back on the x-axis, and then you connect the dots. And let's review. I have a vertical stretch by 2, so now the amplitude is 2, And then I had a horizontal stretch by 3. So then now instead of a period of 2 pi, I have a period of 6 pi. But notice that the sine wave only happens once. And that's the definition of a period. And next we will take a look at a similar example with the cosine. Identify the transformations. We have then a reflection over the x-axis, and we have a vertical translation by 2. That plus 2 is not in parentheses with the x, therefore it is a VT. Notice that we have no change in the amplitude because for the parent graph it's 1 for cosine, and there were no vertical stretches or compressions. And then because there were no horizontal stretches or compressions, the period remained unchanged. Notice how I'm setting up my graph this time. The usual for horizontal, but look at the vertical. So usually it's an amplitude of 1. But now because I have a vertical translation of 2, 2 plus the amplitude of 1 will max me out at 3 with a range of 3 to 1. And then my baseline, kind of like the new x-axis, will be in the middle. Drawing a horizontal dashed line will help you orient your points. So now that we've taken into account the vertical translation up by 2 on the y-coordinates of the periodic function of cosine, now I could take this as my reference point and realize, well, cosine usually, well, at 0 is going to be 1. So it usually start up 1 unit above, or whatever the amplitude is, that baseline, this new x-axis. But this time, instead of starting here, 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 etc., we have a reflection over the x-axis where this baseline is that reference point. So instead of starting here, we have to start below. So the points this time look like a mirror image of the parent graph version. And if you're concerned about how I did the vertical translation first and then avoiding the order of operations by then following it with the multiplication, what technically happens first is the reflection, and then you bump up everything by 2. But I'm trying to have a recipe for these where you kind of always figure out the baseline, and then from there you figure out your stretches as well as and then the vertical translation is already taken care of because you just created a new reference point. I know it's difficult to draw, but practice so that you could make this wave-like pattern and it's not looking like a V. And this then completes our opposite of cosine of x plus 2 with an amplitude of 1, a vertical translation of 2, and a reflection about the x-axis. Oftentimes, you need to talk about periodic functions happening more than once in a given period of time. So this is known as frequency, and that's the number of cycles in a given period. So for example, this is 1 cycle in 1 period. In physics, for example, that period is going to be time, and the standard measure of frequency is known as hertz, spelled H-E-R-T-Z and abbreviated as capital H lowercase z, and is named after a gentleman with that last name who was the first to convincingly prove that the electromagnetic wave existed. And hertz are always defined as 1 cycle per second. So in the first example, we'll use the given information to graph a sine function and find the frequency in hertz. And often you'll find that trig functions of sine and cosine will represent waves in applications. So here, sound, which is a wave, has a period of 0.002 seconds, so it's really fast. and an amplitude of 3 centimeters. Set up the graph the way you normally would, a periodic function, splitting the x-axis into 4 equal parts, and then the vertical axis for setting up in preparation for your amplitude and your range. So we have a period of 0.002 that we need to break up into 4 parts, so I'll divide that by 2, etc. Period of 0.002 seconds. Half of that is 0.001, half of that, and then the addition of these two is that coordinate. And it's sine, so I start at 0 and then go up the amplitude, back to the axis, down to the amplitude, and back to the axis. And that completes our sinusoid graph that represents the sound wave propagating through space, where it takes 0.002 seconds for it to cycle or to repeat again, and its amplitude or intensity has enough energy to make this distance 3 centimeters. And now we need to find the frequency using the following formula. Frequency is equal to 1, as in 1 second, divided by the length of the period. So that will figure out how many of these waves or cycles happen in 1 second. In this problem, the frequency then equals the following. The last portion of the notes is about phase shifts. So that's specifically horizontal translations. We have to also answer these accounting for all x-intercepts using the idea I introduced at the beginning, where because these are periodic functions, we have to include n, which is in the set of integers, and that's better, which happen every pi on n for sine and pi on 2 plus pi n for cosine. So in this example, using sine of x as a guide, we'll graph the function and then identify the phase shift as well as all the x-intercepts. Like before, we'll start with part B, identifying that we have a ht of pi on 4, inner invert, horizontal translations, and then we have a phase shift of pi on 4. Now normally with sine, we have x-intercepts every pi n, so starting at 0, and then again at pi, and then 2 pi, then 3 pi. But now, because we are shifting the entire graph horizontally to the right by pi and a quarter, then starting at pi and a quarter, then we start tacking on the pi n's, giving the following graph, which you'll notice I will give a lot of space in the left of the y-axis as well, and include more than one period to emphasize the phase shift. So because I'm a little crowded, I had to stagger above and below the x-axis with my coordinate markings, but notice that the period has not changed because there is no horizontal stretch or compression, so I'm still working with 2 pi. However, in starting at 0, I'll have to start in between here, or pi on 4 to the right. And then from here, I go pi on 2, which then actually brings me to here. And because this is sine, I go up 1, and then down, down, and then a little past pi on 2. And then I do that in the same direction. Connect the dots, and you can see that it's the same sine function that we've worked with. However, there's a phase shift here to the right. And to emphasize that it just doesn't start, because it's not starting at 0 here, there's a little bit of a gap, then we just put one more cycle to the left. So this is typically how you will see a problem with the phase shift graph. Now to close, how could sine be shifted so that its graph looks like that of cosine. Think about that for a moment. So cosine of theta is the same thing as sine of theta, except that it has a phase shift of pi on 2. So in other words, when you are at sine of 0, it equals 0. But then for cosine, sine of 0 is 1. So then if you horizontally translate this to the right by 1, you would see that. Looking at a graph of the two side by side on the first page of this video visually shows that.